Hello everyone, my name is Ayana and today, together with my colleague Zangar, we will present our paper entitled Event-Related Spectrogram Representation of EEG for CNN-based P300 Speller. I'm a research assistant at the Applied Signal Processing Laboratory at Nazarbayev University located in Nur-Sultan, Kazakhstan, and a first-year PhD student at the Department of Mathematics of University of Manchester. My colleague Zangar is a research assistant and third-year student of Electrical and Electronic Engineering Bachelor Degree Program at Nazarbayev University. This paper was written under the supervision of our co-authors, Professor Prashant Kumar Jamal and Professor Mohammad Tahir Akhtar, both working at School of Engineering and Digital Sciences at NU.
Good evening all. In this slide you can see the outline of today's presentation. Introduction of presentation will start with information about project background and main information about P300 Speller and EEG feature classification. Then we will introduce information about EEG dataset, spectrogram generation, and types of spectrogram used for classification, intertrial coherence, and event-related spectral perturbation. In slides 17 and 18, we will give information about convolutional neural network and CNN ensemble that was used for classification in this project. Slides 19 and 20 will contain results of the classification and then we will conclude the presentation. To begin with, brain-computer interface is a system which records and processes the signal of the human brain activity for enabling the interaction between the human and the computer-based device. BCI devices are frequently used in medical diagnosis or even in gaming industry. But the most popular area for BCI systems is assisting and rehabilitation devices, which help people to control wheelchair or robotic limb processes using brain signals. Brain signals can be recorded using different techniques. The presented table shows different neuroimaging methods and their properties. Compared to other neuroimaging methods, electroencephalography or EEG turns out to be the best option for BCI systems, due to its non-invasivity, portability, and high speed of data acquisition. EEG-based BCI systems may use three different experimental paradigms, which are motor imagery, event-related potential, or steady-state visual evoked potential. MI paradigm is mostly used for muscle rehabilitation BCI systems, or robotic prosthesis, as it detects the frequency change of brain signals depending on the muscular activity of human. ERP paradigm represents the EEG signal as a sequence of voltage peaks, or ERP components, naming them by their sign and latency. The last paradigm is the phenomenon when the human is stimulated with visual stimulus of the frequency up to 75 Hz. The frequency of the brain signal in the visual cortex is detected to be the same as visual stimulus. For BCI spellers, ERP paradigm is preferred, as it will not cause eye fatigue as SSVP. If SSVP is used for speller systems, each symbol presented to the user would need to be intensified with different frequency, which is not very useful for such a big number of symbols.
Classical ERP-based speller is called P300 Speller as it uses positive event-related potential deflection detected at about 300 milliseconds after the target visual stimuli. Its concept was proposed by Farrell and Donching back in 1988. It enables paralyzed people to communicate with the outer world. The rows and columns of classical P300 Speller are flashing in random order one by one, so when the column or row containing the chosen by user symbol is intensified, a sharp positive voltage peak would be detected 300 milliseconds after its flashing. For instance, if the user is concentrated at the symbol P, then a sharp P300 component will be detected only for row 9 and column 4. To extract these ERP features and classify them as target or non-target, there can be many different algorithms and methods used. It should be noticed that ERP components can have different voltage amplitude and different latency for different people. That is why classical P300 speller usually has to be trained for each subject separately. Such training takes a lot of time and it is uncomfortable for the user. So the objective of this work is to design the best features extraction method for subject-independent speller. Classical method used for P300 spellers includes data dimensionality reduction techniques, mainly principal component analysis, independent component analysis, or blind source separation. Nevertheless, classical method is too subject dependent and usually requires separate training for each user. So over the last decade, machine learning approaches have been frequently applied for BCI spellers. For instance, support vector machine, Gaussian mixture model, k-nearest neighbors, and other classical machine learning models. Deep learning and neural networks became a hot topic for any research sphere, and BCI research is not the exception. For P300 Speller, convolutional neural network and long short-term memory networks are mainly used. Another new type of classifiers applied for EEG classification are geometry-based classifiers, which mainly use Riemannian geometry or Euclidean data alignment. All of the classical approaches have their own advantages and disadvantages, but when using them for time series classification, it is crucial to consider the length of EEG vectors, sampling frequency, and other parameters which can vary depending on chosen sensor and data acquisition properties. Thus, in order to achieve better performance, it was decided to transform EEG time series into images which can be easily classified by convolutional neural network. It is assumed that frequency spectrogram representation can achieve better performance, and a universal CNN can be used to classify images of EEG spectrograms without considering different data acquisition parameters such as sampling frequency or number of EEG channels. It is also claimed that spectrogram representation covers all frequency bands of EEG, which can improve the classification results. The dataset containing amyotrophic lateral sclerosis patients' EEG samples is used for generating EEG spectrograms and further training and testing. The dataset provides 8-channel data, and the electrodes can be seen from the figure presented. The EEG signal had been low-passed and denoised by the dataset providers. The data is collected from 8 subjects suffering amyotrophic lateral sclerosis aged from 40 to 72 years old. Dataset represents the data collected from 5 male and 3 female subjects. There are different types of ALS, spinal and bulbar. Spinal onset ALS usually starts from paralysis of the limbs of the patient, and in bulbar onset ALS, breathing and speaking muscles are the first to be affected and paralyzed. People older than 65 years usually suffer from bulbar onset ALS, while younger patients are commonly diagnosed with spinal onset. This tendency can also be noted from the presented table.
There can be different types of spectrogram generated from EEG signal. One of them is intertrial coherence, which splits EEG signal and computes its fast Fourier transform coefficient, with the further normalization and mean of these values. ITC can be obtained channel-wise or by using independent component, resulted from ICA. The obtained ITC plot shows that it provides good pattern seen for oddball paradigm with a corresponding frequency domain representation of P300 component. After submitting the paper, it was found that the generated ITC spectrograms are different from the classical ITC definition. Thus, the generated ITC is just a type of spectrogram representation of single trial. Another type of spectrogram representation for EEG signal is event-related spectral perturbation. RSP is obtained by using FFT or wavelet decomposition using further moving average filtering. It can be obtained from event-related spectrum by subtracting the baseline before log averaging. It is seen that without baseline, event-related spectrum does not provide any patterns, but when the baseline is removed, patterns are clearly seen, so it is efficient for P300 component classification. RSP covers all frequency bands and can be obtained channel-wise or by using cross-channel data. Different baselines and transform methods can be used for ERSP generation. The presented plots are obtained by using standard deviation baseline with 2 different time frequency transformations applied. Another baseline is maximum divisive baseline, which subtracts the maximum value from event-related spectrum. It is seen that the patterns provided by wavelet decomposition have better time frequency resolution, as it slides non-uniformly along the time and frequency axis, while FFT provides uniform time-frequency grid. Spectrograms have been generated by applying the divisive baseline method in ERSP and FFT in both spectrograms, using the EEG Lab toolbox. The spectrograms are separated into two classes, the first including target stimuli recording and the second containing only non-target stimuli.
The proposed classifier is based on a classical CNN architecture. The spectrograms are compressed to the size of 51 to 46 RGB images, which are fed to the CNN. The first layer of the network is a convolutional layer, which is followed by the maximum pooling layer. Each hidden convolutional layer uses rectified linear unit as an activation function, and there are two combinations of convolution and pooling layers, which are connected sequentially for efficient dimensionality reduction. The second pooling layer is followed by the linear fully connected layers. The last layer's activation function is a softmax function. The softmax normalizes the output of the last layer, translating the output values into a probability distribution. As a result, the network outputs a vector of two elements, where each element represents the probability of the input EEG spectrogram either containing the target P300 component or not. The same CNN architecture is used for two models, CNN1 and CNN2. CNN1 is trained on the training set of ERSP spectrograms, while CNN2 is trained on ITC spectrograms. Two CNN models with the same architecture are trained on different types of spectrograms. Both types, ERSP and coherent spectrograms, are obtained from the same EEG time series data. The models are combined in an ensemble voting classifier CNN-ENS. The classification results of the ensemble average model is the average value of the inner CNN classifiers. Training set contains 1,920 samples of ERSP and the same amount of coherent spectrogram samples. Test set contains 656 samples of each type of spectrograms. From the plot of log loss obtained during the training process, it can be seen that the loss decreases with the number of epochs, meaning that all of the models are learning properly. It is seen that the loss provided by CNN-ENS is something between the result of CNN1 and CNN2, as it considers both types of spectrograms. It is seen that the proposed models generally achieve about 80% of accuracy on test data. The proposed model provides high performance if compared with classical EEG time series classification methods, which are linear discriminant analysis and stepwise linear discriminant analysis. Spectrogram representation turned out to be more efficient on both validation and test. Stepwise LDA provides slightly better results than LDA, but still it reaches only 77.5% of a S-score on test, while the classification of ITC and ERSP spectrograms using standalone CNN achieves more than 78% and 81% respectively. According to the experimental results, ERSP seems to be more representative than coherent spectrograms, as CNN1 reaches almost 82%, while CNN2 with the same architecture achieves less than 79% of accuracy when tested on coherent spectrograms. Usage of both spectrograms enabled to achieve 88% of accuracy. The validation for ERSP reaches 87.34%, while coherent spectrograms provide only 85.61%. Thus, it can be assumed that ensemble learning may be more efficient for some data distributions. Summing up, spectrogram representation is more efficient than single-trial time series EEG. Using both ERSP and ITC-like coherent spectrograms improves the accuracy, and ERSP provides better results than coherent spectrograms for ALS patients' data. However, there are possible limitations. For instance, classification using ERSP and ITC obtained using several trials may provide different results. Also, ensemble learning is computationally more complex, and the possible solution for that is using parallel computing. It is assumed that using both feature maps from ERSP and ITC in a single dual-input CNN architecture may provide better results than the ensemble model. Thus, the features of both types of spectrograms can be concatenated into a single vector before processing by the linear layers. Apart from that, it is planned to use data from patients with cerebral palsy or peripheral neuropathy to verify the proposed method for other types of patients.
This work was supported by the Faculty Development Competitive Research Grants Program of Nazarbayev University under 2 grants, numbers of which you can see on the screen. Here are the key references used in our paper. Thank you. If you have any further questions, please do not hesitate to contact me and my colleague by the email provided in the slide.